or any of that stuff. Let's see, what did I want to do? What else do I have to do? I will share screen. We're going to do mostly coding today. Was the second homework is due next Sunday, or was it just due this Wednesday? Okay, I can probably, if you guys want, I can extend it. I'm always happy to extend. I just, on Wednesday I will have to put out the third homework, but I'm happy to extend always, you know, especially in this class. You know, I want you guys, I don't want your learning to be impeded by time constraints unless absolutely necessary. So there was one slide that I wanted to.
Sorry, I just have a question.
Yeah.
You record the Zoom.
Yeah, I'm sorry, I haven't posted. So I've started a YouTube channel.
I see.
And I've yeah, I know. I know, because right now there's only one lecture on it. Let me show you. This is the name of the channel. Here it is.
Okay.
Okay. So all you have right now is, so what I have to do is I have lectures on the cloud. I have on Zoom, the Zoom cloud. I have to download them and post them here. So I am going to post them all. I'm going to try to remember to do it today, or at least this week, but it is there. And I'll post a link to this channel.
3 views, that's pretty good.
It's right. It's awesome, right? I'm going viral. I am going viral. Yeah. Oh, actually, I'll put it under content. Web link, I guess. If I ever do, my daughter was telling me, my 9-year-old daughter, not the older one, was telling me about, she's like, Daddy, Mr. Beast no longer has the most followers. I'm like, oh, who has the most followers? He's like, some PewDiePie guy. And she's like, but I don't like either of them. I like who is she like? Unspeakable, because he went to a water park for 24 hours and he, I'm trying to explain to her, it's probably fake. I don't think that he actually broke into the water park overnight and like filmed it discreetly. And she was like, no. Anyhow, but if I ever do have a YouTube channel, I'm going to make a point to say you do not have to subscribe to this channel. You don't have to like it. I'm doing this for you. I'm not trying to make money. Did I answer your question about the videos?
Right.
I record everything and I'm going to post everything. I'm sorry that I haven't done it yet, but it is all going to be posted perpetually on YouTube. So we were talking about overfitting, regularization, and hyperparameter. So this curve is very important. Basically every machine learning course will show this curve. So the idea is the further to the right you go, the more parameters your model has.
That's right now you're sharing.
Oh,
you're not sharing the screen, you're sharing with you. I don't know what exactly you want to do.
that's weird. Let me try again.
Yeah, now it's the
Now is this okay? Yeah, it's probably this. Should be mirroring though. So the further to the right you go, the more essentially it's smaller complexity, which in most cases translates to the number of parameters. In some of the newer architectures like LSTMs, the number of parameters is large, but the model isn't actually as complex as the number of parameters indicates, because some of the parameters are like coupled together. So if you change one, think of it as degrees of freedom, but this is a simple model. This is a very complex model. And the idea, the thing that may be obvious to you, but may not be, but that if you keep adding parameters to your model, that you're always going to do better on the training data, even if even if the dimensions that you're adding don't tell you anything about your target variable. The loss function will always go down as your model complexity increases. And so that means that you cannot possibly evaluate your model solely on training data. It is definitely a good sign when you get good training performance. You want that. But the key is to get good training performance with as few parameters as possible. That's the Occam's razor thing. And the way you tune your model complexity is by also having, this was called, again, like I said, now they're calling it validation. It used to be called holdout. This could be test data for the sake of this, what I'm saying. Basically, you have the red corresponds to the performance of your model on data that is not in the training set. And so this curve does not monotonically decrease. This curve will have a minimum in general, and you want to pick this model here. You want to pick the model corresponding to the trough of this curve. Now the challenge always is, how do you know where that is? How do you know what model that is? Well, we're gonna do an exercise in MATLAB today that basically does exactly that, using cross validation and hyperparameter tuning. So you can think of this as, so over here is a very simple model. In other words, very, very, very strongly regularized. And so at the left end, those are models that are too simple. They're not capturing the structure in the data. Over here are models that capture the structure and the noise, because you see that the test performance has the loss or the accuracy or area under the curve has started to get worse. So you want to, this is called, I should have labeled this inside. This is called overfitting out here, and this is called underfitting. And so the idea is that, notice that on the underfitting side, there's not going to be a big difference between the blue and the red curves. The loss is going to be the same. And so that, in a sense, what that means is underfitting is kind of an easier problem to tackle, because if your training loss is high because you don't have enough parameters, at least you know that that's what you're going to get on the test set. On the other hand, if your training set, if your loss if your training loss is very low, but your model is too complex, you won't find out until your model starts degrading. And so what I want to, again, I think that's everything I wanted to cover on this lecture, but I have an addendum that I put together. So that when we start going into the code, you're not lost about what we're doing. Right. So hyperparameter tuning is a big part of supervised learning, any learning really. We're going to use a MATLAB function called lassoglm, which is a good function actually. I like this one much more than MNRFit. Lassoglm is yet another function that can do logistic regression. It can also do different types of regression though. It's pretty flexible. But before we step through the code, you need to just know a little bit about what lasso is and what the elastic net is. You'll encounter these terms in practice. So lasso, the actual name, like the acronym, is for least absolute shrinkage and selection operator. Really not very, doesn't convey anything about what it is. But it's essentially what it is. It's a framework for doing regression with an L1 penalty. So it's sparse regression, basically. And the cool thing about it is that it's not just a specific type of regression. It can handle different types. So, and that includes the two most popular, which are linear regression and logistic regression. So what it does is it allows you, like I said this many times already, it allows you to perform regression without thinking too much about which features are going to be important, because the L1 regularization will set many of the weights to 0. So lasso is a fairly new technique. Like it was first published in '96. So I mean that's relatively recent. At on the time span of scientific knowledge, timescale scientific knowledge, and so MATLAB is a function of lassoglm, which we're going to be using to implement this algorithm. You don't actually have to know how it does it. You just have to know how to call the fitting function. Elastic net is something similar. Is related to the lasso, but it's a general framework. And remember, last class we talked about you can have an L1 penalty and you can have an L2 penalty. So elastic net lets you put in both penalties. So you can remember I said you can make the model have small weights, which is here, and you can make the model have here, and you can make the model have sparse weights, which is here. So in practice, people say, well, I want both. I want the weights to be small, and I want many of them to be 0. So the way to do that is to put both and put 2 penalty terms into your loss function. So you have some loss function L. So let's say this could be for like linear regression, so being just mean squared error, or for logistic regression, this will be the negative log likelihood. And you want to pick the W that minimizes the loss and keeps the L1 norm small and keeps the L2 norm small. So the question is, what is alpha? Alpha is it's a number between 0 and 1. That should be in the slide. I'll try to add it. I'll remember to add it. So let's take the two extremes, alpha being 0 and alpha being 1. So when alpha is 0, this comes out, and all you have is the loss plus an L2 penalty. So that's L2 regularization. Now take the other end of the extreme. When alpha is equal to 1, then this term drops out, and all you have is your L1 penalty. I'm actually going to correct this on the fly because there's two things that are should also be a lambda here. So why isn't letting me? Come on. I'm trying to insert equations. There we go. Just trying to insert a right there. Over, please. Left. Thank you. Yeah, so slideshow. I'm still sharing. I hope I am. Andrew, do you see the PowerPoint on the Zoom? Yeah. Okay. So there's two numbers they have to specify. One is the alpha. Alpha is easy. You just like if you make it 0.5, you're gonna do half L1, half L2. That's all. And by the way, like I said, everyone does this because you don't want to commit to anything. And what this lets you do is this is like keeps you non-committal to whether you want L1 or L2 regularization. And then the lambda is your actual, the strength of your regularization. So if you make lambda very high, then you're going to make the weights will come up very small. We'll verify that in MATLAB. Yeah.
Is there an intuitive way to understand why they have to be controlled by the same variable? Like, why can't I try to minimize my weights and make it as sparse as possible? So why can't it be an alpha and a beta? Why, or like different lambdas or something like that?
Different lambdas. I think people do. I think that is an option. Yeah, I'm sure that there. Yeah, I'm sure it's. I'm sure there's a version of this which is just forget this was lambda 1, lambda 2. That's a good question. I think.
You give someone from your experience, there's often a trade-off from one versus the other.
Yeah, I mean, I think that the strength of the lambda kind of so the magnitude of lambda just kind of depends on the scale of your data of your features X, and so they're going to be in the same ballpark, and so I think this is just kind of a convenient way to because now when you do this tuning, you have to do a search. So this is a two-dimensional search space. Dimension 1 is alpha, and dimension 2 is lambda. And I guess you can do it with lambda 1 and lambda 2. But I put this version of the equation up because that's what corresponds to lassoglm, which is the function that we're going to be doing. But it's totally your question is totally valid. Why don't you just do lambda 1, lambda 2? This is kind of what this is doing. It's kind of forcing you to kind of have the same or
things lambda 1 and lambda 2 equal to 0, right?
Yeah, that's the thing, right? It is. I think it's mathematically equivalent, actually.
Well, here you're forcing that when you increase the L2 penalty, you're decreasing the L1. So I'm asking why are they connected? That's kind of
so, but the question is, if you have, what I'm wondering is, if you have this versus, and let's say, no, just that. I think these two are mathematically equivalent. Like, at least there's a way of, like, if you just do a grid search, I think they're probably mathematically equivalent under certain. I guess I think the reason why like MathWorks has decided to do this is because this it gives the user like a kind of an intuitive parameter for controlling the trade-off between these two. So like some models an L1 penalty will seem more appealing and maybe I don't know, but it's totally a good question. I had the same question actually in the past. Okay, and then how do you actually do this in practice? How do you actually tune hyperparameters? So there's packages out there. I know in Keras, for example, that tune hyperparameters for you. There's different ways, but the basic idea is that you pick a candidate set of values, and then you perform cross-validation for each candidate value. And then at the end, you pick the lambda that gave you the highest test set performance. So why did I do log space and not list? So log space, by the way, so that line log space, I did -3 to 3 to 7. What that means is your lambdas are 10 to the -3, 10 to the -2, 10 to the -1, 1, 10, 100, and 1000. So this is in any real world problem, you will have no idea what the optimal lambda will be a priori. And so what this lets you do is it lets you do a search over orders of magnitude. And there are strategies where, like, let's say that you identify this to be the best, then you can drill down further and do like, point, this is 0.1, so you can do 0.005 to 0.05, for example, in finer steps. But doing logarithmic spacing for the lambdas just makes it easier for you to find the approximate best range for the lambdas. That's why in many cases, I think the example I'm going to give you also uses logarithmic lambdas. But this is critical, that this is where it all comes together. You're going to do cross validation together with hyperparameter together we're trying different hyperparameters, different lambdas. And then the lambda that gives you the best test of performance, that's what you're going to go with in practice. And I will now get my glasses on and switch to MATLAB. And I put together, shared a M file under content that I will now step through. Do I want to share? Yeah, I do. Still want to share. It's called demo over fitting CV, but it's actually really demoing cross validation of hyperparameter tuning. Okay, so does the ovarian data set come on your MATLAB? If not, I'll again put it on block. Okay, it does not. Okay, let me just post it. Wonder why they made the decision to get rid of these data sets from later releases. It seems like a weird thing to even concern.
Ovarian cancer does not
It could be the same. If it's 200, if you have 216 as the dimension of
116 by 4,000 or 16 by 1 is cell of GOP.
oh, okay. Hold on. I may have. I'm just gonna. Yeah, I'm gonna post the one I'm using. Something tells me, oops, something tells me that what I did in a previous year is truncated the data set and used it, the truncated version. But the truth is you can run this code on any, this code will run on any data set. You just have to specify X and Y at the front. Okay, so what we're gonna do here, all of the data, and first just inspect. So I have 200 let me see. Sorry, what is it called for you?
It was ovarian cancer.mat.
I got it.
Okay. All right. All right. So the data here has 216 examples, right? Because that's the first dimension of X and Y. And then we have 100 features. So if we take a look at our features, this is what they look like. So these are features, these are examples, and Y we can just, oh. Okay, so these are the features, and then ovarian targets comes into us as, again, this 2-row format. So the size of it is 2 rows by 216 columns. So again, the rows are probability of that each of the example comes from one of the two classes. So for example, the fact that you're seeing all the examples that you're seeing on the screen, the second value is a 1, just means that comes from the second. And I don't remember, I'm sorry, I don't remember, and there's no help file here. I don't remember what this data set is trying to do, other than that it's ovarian cancer and it's, it's either benign, malignant, or tumor, no tumor. We can do the mean of Y, to see what our class prevalence is. So 44% of the examples are positive. So again, it's a very balanced data set. So what I did here, so one change from the last demo is that lassoglm needs zeros and ones, needs Y in 0 or 1, right? Whereas MNR fit wanted 1s and 2s. So basically what I did here is I took the second row and compared it to 0.5. So the probability is bigger than 0.5. That's a malignant tumor example. So now you have, if you execute the cell, you have X is 216 by 100, Y is 216 by 1. And now we're ready to try and figure out how to fit this model with logistic regression with regularization. So first thing we need to do is define our set of candidate lambdas. So what I've done here is I've started, I've started with one over 1,000, and I just added. So what I did is 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, and then 1, and then I also added, just for good measure, I doubled all those values. So I have 7 candidate values that I'm gonna want to scan, and for each of these values, I'm gonna fit this model, do a train test split with cross validation, and see which of these values is going to give me the best performance. So the next thing I'm going to do is create my train test split. So in other words, figure out which example is going to be creates the cross validation indices for you. So there's a convenient function called cross val ind. So let's go ahead. So if you do help cross val ind, first of all, I'll pull up the documentation. So it takes 3 arguments. The first argument is a method of cross validation. So it can either be k-fold, which is what we're going to be using. So that's what I talked about last class. You split up your data into, say, 5 folds. there's something called the holdout technique, which is it's just one, like you just have one train test partition. So if you make the parameter 0.5, you'll have 50% of the data in the training set and 50% in the test set. And then I told you about leave one out last time, or leave me out. So it's similar to holdout, except that you specify the number of samples to leave out. So this can be one, for example. I've never used resubstitution. I have no idea what it is. And what is, and it's the number of examples. And M is the parameter that controls how you use CV method. So this actually works, but I think it used to be you called it like this, but it really should be this. Let me see. Okay, so now I've called this function and I'm going to show you the output. Okay, so this is the output of my CVNs, and it's 216 by 1. And the values of CV, what are the unique values of CVNs? Well, they're the integer is 1 to 5. So what does that mean? I have a vector of 216 values, where each value is an integer from 1 to 5. And so what this function has done is it has put every example in the data set into one of 5 buckets, which is convenient because now, for example, let's say that you want to train on 80% of the data and test on the remaining 20%. What you will do is select bucket 5 as a test set and select buckets 1 through 4 as a training set. And so this cross-val in function, which I called here, I've told it that I want to do k-fold cross-validation. I want to do it on, this is 216. I want to do it on 216 examples. And I want to have 5 buckets. I want to have 5 folds. And so it means that you don't have to do the random number generation. Like you could have just generated random numbers from 1 to 5, 216 times. But this also guarantees that, for example, you can see how many examples fell into each bucket. And it's not going to be equal because I don't think this goes into, one of them is going to be bigger. It's actually fold number 4 has the extra example. Okay, so this is, and here is the cross-validation loop. So we're going to have, in many cases, you have to do like a nested for loop where you have one loop for the lambdas, one loop for the cross-validation fold, and then a second loop inside of that for the lambdas. But the nice thing about lassoglm is it lets you, and I'm going to explain this in just a few minutes, it lets you test multiple lambdas at the same time, which is really nice. And so I only need to have just a single for loop here to do what I need to do. But before I get there, let's look at how we actually, let's go look and see how we actually use the CVINs parameter, which again was different, showed here. So I've created my cross-validation indices, and now I want to create my training set and my test set. So at every one of these 5 folds, I'm going to look at my test set is going to be every example where that was assigned to bucket F. So for the first iteration here, when F is equal to 1, the test set are all the 43 examples that got assigned to bucket 1. And the training set is everything else. It's buckets 2, 3, 4, and 5. And here's where I actually slice my, so X and Y is all the data. And now X train and Y train are just gonna be, oh, what happened? I'm gonna run this. Okay, so who can guess what the size of X train and Y train are? Yeah, yeah, it times 4/5. Yeah, right, exactly. So it should be, so it's 100, right? So 173 over 216 will be 80%. So every example still has all the 100 features, but now there's only 173 of them. And then size of Y train is just going to be 173 by 1. So now you have a separate training set. And here is where I want to spend a little bit of time just looking at the documentation of lassoglm, because it's very flexible. And what that means is that you have to pay attention to how to supply the arguments to the function. So the X and the Y are obvious, right? The X is your features, it's your predictors, and the Y is the thing that you're predicting. However, but there's also something called the distribution parameter. So let's scroll down. So I don't think I'm going to teach you generalized linear models in this class because it's mathematical. I'm trying to make this class more practical, but I did in the past. But GLM, generalized linear models, is just like a mathematical framework that lets you do different types. Basically, it handles different distributions for the thing that you're predicting. So if the thing that you're predicting is a Gaussian, then, and that's the default here, I think, then the GLM just basically the GLM says you should do linear regression because your Y is a continuous continuous Gaussian. Now binomial means, binomial is what the situation we're in. Binomial is your target variable takes one of two values. I think it's also sometimes called Bernoulli, but they call it binomial. And so that's what we are. And so if you want to be, if you're regressing onto a Poisson process or a gamma distribution, you can use the same function. But the two key ones are normal, which makes lassoglm do standard linear regression, but with this regularization, which is cool, and binomial, which leads to logistic regression. And so here's an example of how you would call lassoglm. So this would be regress X onto Y, where it's assumed that Y is a Poisson process. So Poisson process is a counting process. So Poisson process, we don't get into it here, but it counts number of, it's actually, yeah, it counts the number of occurrences of some event in a short time window. Alpha is the thing that that was on the slide. So it's the weight, it's the balance between L1 versus L2. More jargon for you. I'm sorry, ridge is another word for L2. So lasso is sparseness is L1, ridge is L2. And so we are going to set, we're going to set to the default here is to make it 1, which means we're just going to do, the default here is 1, which means just do the sparseness. Don't do any ridge. In the code I have, I think I said it, I think this code actually, like when you set it to 0, it actually crashes. That's why I made it, apps is a very small number. So in this code, as I gave it to you, I made the alpha very small, which means that I'm doing just L2, but we'll also run for L1. It even says alpha close to 0 approaches ridge regression. And then the other key parameter here, we're doing the cross validation ourselves, but they actually give you an option for, they'll do the cross validation for you. But the other key parameter here is the lambda. So the lambda, as you can guess, it's a vector of non-negative values corresponding to your candidate hyperparameters. So because this is a vector, what this function is allowing you to do is to, I'm gonna go back to my code. So my lambda is this this is my lambda here. It's just these 7 positive constants. And so I'm telling this lassoglm function to do regress x onto y, or in other words, predict a y from x. Y is distributed according to a binomial distribution, which is binary, basically 0 or 1. I'm saying I want full L2 regularization. So I want to make the weights small. They don't need to be, I don't need to have any of them being 0. And I want you to fit a model for every one of these lambda parameters. So this is the key function here. I'm going to step in the next line, and I'm going to then show you the output of B. Okay, so no warnings. That's good. If it encounters problems, if it sees something in your data it doesn't like, it will tell you. So now my size of B is 100 by 7. So does anyone want to take a guess as to why it's 100 by 7? Why is the output of lassoglm 100 by 7? What are those 2 dimensions corresponding to?
Telling you the best value for each feature. So that makes no sense.
It tells you the coefficient for every, it tells you the weight of every dimension of your classifier. Like your
I mean, wait, is 100 the features? Or
there's 100 features
Alright.
in your data, and then the 7, yeah, exactly. There's 7 W's basically, or I don't want to show my tax return. God damn it, preview.
we don't need to know.
Yeah, I know that's some hacker is gonna figure out my social security. Yeah, my daughter was applying for FAFSA and she needed my tax return information. Okay, where was I? What did I want to show? What I wanted to say is that, like, for, yeah, it's this W basically. Our W here is 100 dimensional because we have 100 X's. So each one of these columns of the matrix B is a separate model, one for every value of lambda. And so what I want to do is, so there's a lot of things we can do at this point, but the first thing I want to show you is, let's actually look at the first 10. I'd like to show them as a table. Trying to show you the trend. So I wonder if this will work as an image. Sort of. Yeah, it works actually. What I wanted to show is that the weights are high, the weights are larger for models 1 and 2, and they get progressively smaller as we go into 7. So that is what the increasing lambda makes the weights smaller. And so, like, if we do, for example, mean apps B across 1, what you're going to see is that the average value of the weights is going to go down as lambda gets bigger, which means that this is very little regularization. This is a little bit more regularization. This is, and then this is very regularized. And so now I have 7 models. And the kind of annoying thing about lassoglm is that it puts the intercept term in a separate variable. So B could have been 8-dimensional, but lassoglm, there's a separate, there's a second output of this function called fit_info, and fit_info is a struct that has many different pieces of information, but it also has the intercept terms for each of your models. So these are your constants. And so now what I want to do is take my training data and I want to apply it to the classifier that we just learned. So this is important. So what I'm doing here is I'm projecting my training data onto classifier B. I'm adding, so if I do this, right? So now I have 7 kind of predictions for every example, right? So these are what's in the parentheses here is the soft prediction of benign or malignant. If that number is bigger than 0, we're going to say malignant. If that number is smaller than 0, we're going to say benign. And that's what this conditional is doing.
You're doing the training again?
No, I want to measure training performance. I'm not fitting again. So here what I'm going to do, I'm trying to convince you that the training accuracy is going to be very high. And so now the size of Y train pred is 173 by 7. And so what I have to do is the true value of the labels in the training set are 173 by 1. So what I need to do is basically replicate this 7 times and compare it to the prediction. So if I only wanted to get the accuracy of the first value, the first lambda, I could go just take the first column and perfect accuracy. Because they're probably all going to be, so as you get, and so, but what I'm going to do is I'm actually going to do what's called a repmat stands for repeat matrix. Basically, I don't want to have to do a for loop across the 7 lambdas. I want to vectorize this operation. So what I'm taking my labels and I'm just repeating them 7 times so that I can compare the predictions for all models to what the ground truth was. And now I'm going to have a training accuracy vector. So this is the accuracy of model 1 on the training set, accuracy of model 2, all the way through model 7. As expected, the accuracy is getting worse with more regularization because the more regularized the model, the simpler it is. So now let's go. Now what we really care about is the test set performance. So first we need to create the test data. So we do it the same way as we did for the training data. And now let's take a look at test set is just 43 examples of 100 features, and the labels are 43 by 1. I'm going to do the same thing as before. I'm going to now compare, I'm going to project my unseen test data onto the classifier. And now the size of Y test pred is going to be should be 43 by 7, right? So you have one prediction for every, sorry, you have 7 predictions for every examples. And now the moment of truth, this is where, like, if you've been developing a model for weeks or months and you finally you finally get to the point where you've coded everything and the cable dies. You should get the VIA system in here. It's not perfect, but okay, so I'm gonna measure my test accuracy now. Okay, so here we go. It's not very not very illuminating for this fold. So if I do figure stem test act, you'll see the performance for stem is probably not a good one because it's to plot with just a marker. I'm trying to show you that what the right, so so
Range are so small.
the rate, yeah,
It
and
looks like the graph is such steep data. It looks like, oh, they're miles apart.
well, so there's a couple things though I'll say to that. Yes, but in many in like a lot of these state-of-the-art machine learning data sets that are used, a percentage point or two on the data set is actually a huge deal. It's kind of funny, like the people will compete for like an extra 0.5% accuracy. But the second thing I'll say is that you know, these data that it's difficult to demonstrate some of these concepts on kind of synthetic data because synthetic data is usually very clean. And so let's continue on to the next fold and see if we get something that's a little bit, basically what this plot is saying is that as long as you don't pick the 5th lambda or the 7th, you're going to get optimal performance. But
Question.
yes,
This for loop goes through for cross validation all through 5 seconds.
Yeah.
How do you select like your best lambda within each one?
oh,
So, like, if
you
you're
average
at
over the 5.
35 points, you average.
You average the performance over the 5 folds. So do this again.
And then we talked about it a little bit last week of like, how do you get your final lambda?
Yeah. So what you will do, what you will generally, like you'll do this to figure out the best lambda, and then you'll generally fit a model on all the data with that lambda.
So the graph has 7, but there are 35 lambdas in theory, right?
No, it's the same lambda in every fold, but there's 35. Let's see.
Like performances.
Yeah, right. Exactly. Yeah, there's 35 performances. So here we go. Let's look at the second. Let's look at the performance on the second fold and see if it was any, if it looks. Oh, there you go. So here, actually, this is interesting. Here on the second, and this happens all the time in practice, where the different cross-validation iterations don't agree. that is very, very common. So here, actually, on the second fold, we got the best accuracy with a lot of regularization. It's doing the 3rd iteration now. Did it do it already? Yeah. And let's do the 3rd. Again, that was just a nice segment of the data. It's the 4th. And we'll do the 5th. Oh, this is what I was hoping to see for everyone. This is perfect for a teaching standpoint. Not you don't care, but I care about.
The overfitting graph.
Yeah, this is the overfitting graph right here. So here there's a clear And the reason it's hard to show also is you normally have way more lambdas than 7, but it will take a long time. So this is what I was hoping to see, is that there is some range of the lambdas, and you can actually plot this as, if I put lambda here, right, you can actually, oh, log space. Will this work? Yeah. And so this is your actual graph, where the bottom here is lambda, the horizontal axis is lambda, and the vertical axis is test set performance. So here you see that not enough. So this is the overfitting range here, where you get 93% on the test set because you've overfit a little bit. If you tune the lambda just right, you get almost 96%. And here this is too regularized. So this is an example of what usually happens in the real world. So what I'll do now is, so I'll just continue until the end. Or did I think I heard.
You don't touch the alphas, you use the logical.
Oh yeah, in practice you will, but I didn't want to do a 2-dimensional, but you absolutely do in practice.
And you do them separate, or you have to like do like all over again?
It's just a 2-dimensional. Here you have a 1D for loop. And then let's actually just look at this before I'm gonna do L1 before we leave. I was gonna show you training and test set accuracy. For so average over the folds, or what size of training? Right. So didn't on this, and every time you'll run this, you'll get a different result just because of the random number generation. But here what we see is that the training performance as expected gets worse as lambda increases as expected. But the test performance, I was hoping to see an optimum somewhere out here, but it didn't quite work out. So here, if you were running this, you would still pick either the first lambda or the second. They gave you the best. They gave you the best performance. Let me do this again, but this was L2. Oh yeah, and the other thing I wanted to show is that show you the weights that came out of this. Notice that not many of them were exactly 0, right? Let's run this now with L1 instead of L2, and at the end I'll run this, I'll wait, and at the end I'll show you the weights, and hopefully oh, there we go. There's a little bit of an optimum here. Not a huge difference, but the one thing that's obvious is that if you do too much L1 regression, you really degrade performance. And so now if I do so the 0 will be a good color map for zeros, maybe jet. Yeah, you can see it here actually. So 0 corresponds to this yellowish green color, and notice that A lot of the weights are exactly 0. So let me just, so this is like, for example, for the highest value of lambda, so this, if you over regularize, the model converges to an all 0 model. You see that this, the stronger, let me actually put this into the script because this is useful. X label. Right. So what you see is in L1, most of the even the first lambda, most of the coefficients are 0, and I think maybe we'll see that with a stem plot. Yeah. Right. These are your model coefficients for the first lambda. You notice that many of them are exactly at 0. This is a good thing. This tells you that you can discard those features. If I run the same thing, I'm going to run this with L2, and you'll see that oh, they're so stupid. You're going to see that stem plot will no longer have all those zeros. And so from an interpretation standpoint, where's the stem plot? Right. What's that? The big
Performance for the one was better.
Oh, was it? That's interesting. I can't remember what.
It was 94%.
Okay. So this is L2. So yeah, I mean, I love L1 personally just because of this is kind of annoying that you get all these small weights. So you have to use all these features, even though they're probably not adding a lot. And so this is why in general, L1 is still probably, it's more popular in research. It's also, I think, more popular in practice. Thank you guys. I will see you on Wednesday.